Okay, good morning. So this is the last lecture on the detailed routing. Uh, we shall be looking at one more technique for channel routing. Then we shall be moving to some other things. Okay. So we discussed about the different types of two-layer routings yesterday, up to yesterday's session, in the detailed case. Okay, first we will have a comparison of this, and then I'll start with the last type. Okay. That is the one more technique. What I was just saying about. Okay, one more technique for channel routing that will be that we shall be moving to. Then we'll be moving to some other very specialized routing techniques for only one type. That alone we will discuss. Okay, so today's session I will not be going in detail because all the algorithms are a little bit involved there, and I do not intend to discuss the complex algorithm as part of today's discussion. So rather I shall try to motivate you, maybe try to make you appreciate what the problems are, and then with some illustrations maybe I'll try to explain how the problems are typically solved. Okay. So not like what we did yesterday or day before yesterday. So as I told you, first we will let us compare the channel routers that we have already seen. So you have the left edge algorithm, the extension left edge algorithm, the extension of the left edge algorithm, then the extension of the left edge algorithm with the dogleg. Then we discussed about net merge algorithm. Then we discussed about the greedy algorithms. Okay, so all these are grid-based models. All these models are grid-based models. This LEA basically does not support doglegs. Okay, but all others support dogleg. And if you see vertical constraints, the vertical constraints basically LEA didn't support, but the extended LEA support that, and all others support that. Okay, so but other support slightly constraint, which means there is no cyclic. Okay, but I have included cyclic in a separate thing. Okay. The greedy algorithm, all these things. Okay, all these things support this. So you have the cyclic constraint in VCG. You have two alternatives to. So this greedy algorithm support the cyclic constraint. All of this don't support the cyclic constraint. Okay, that's why we say that we conclude. Okay, greedy algorithm, even though it is a very simple algorithm, it is a powerful technique. Okay. So either you can move, but if you are having the greedy algorithm, cyclic constraint, one thing is you can use a greedy algorithm. Okay, or what you can do is you can move some of the terminals around if possible, so that you can break the vertical constraint, make some of the edge non-existing. For example, what I am trying to say is one was on top of two. Okay, so here is two, and exactly at the top I am having one. I assume that these are standard cell layout, and the whole grid is nothing but the channel. So here I'm having the channel one, the terminal one, and here I'm having the terminal two. So if you are able to move two by one position, maybe by one column, okay, so that there will be no connection below one. So this two will become zero here. Okay, that 1 to 2 edge will go out. Okay, in the graph, in the vertical constraint graph, there will be a edge from 1 to 2 with arrowed edge, the arrow pointing towards or incident on 2. Okay, that edge will go out in the vertical constraint. So if it is possible to move such terminals around, we move them, which means that we are moving some of the cells around in the standard cell layout. If it is allowed, then we'll have to we can easily do that. Okay, which means that cyclic constraint can be removed. If one of the edges is removed, then automatically the cyclic constraint is removed. Okay, so that is allowed. If it is not allowed, then we will have to go for the greedy algorithm, which can handle the doglegs and also the cyclic constraint in VCG. So next, today we shall briefly talk about the 3-layer channel routing algorithm, without going into much detail. Where of course there are several approaches are there. but we shall be looking at one possible approach. Okay. Uh, uh, Let me talk about the approaches first. There is an extension to the net merge Yoshimuraku router. Okay, we talked about that Yoshimuraku routing algorithm or net merge routing algorithm. So there is other approach which starts with a two-layer solution and extends that into a three-layer solution. Okay, two-layer solution is such a solution, extends that into three-layer solution. And there is a hybrid router, okay, which considers horizontal, and also vertical, both combined. Okay, combine both of them together and try to complete with the three-layer channel routing. Okay, let me talk about that only one algorithm, that is how we are going to extend the second one, HVH routing from HV solution, that is extend the two-layer solution to the three-layer solution. So let us try to see this. So the method we briefly here we are talking about is the one of getting a three-layer solution from the two-layer solution. Conceptually, this approach is similar to the Yoshimuraku algorithm, okay, or the net merge algorithm. So what we do here is we systematically transform a two-layer solution into a three-layer solution. Systematically transform the two-layer solution into a three-layer solution. So what happens in the three-layer solution? We have three metal layers: metal layer 1, metal layer 2, metal layer 3. Now in two-layer solution, I have only M1 and M2. Put all the horizontal segments on one layer, say M1, and all the vertical solutions on another layer, say M2, or the other way, HV or VH accordingly. Now in the Yoshimuraku algorithm or the net merge algorithm, we were trying to merge two or more nets to form a composite net. That's what we discussed in net merge algorithm. Okay, such that all of them would be laid out on the same row. Okay, uh, let us say some horizontal track. Okay. But now when we think of a three-layer solution, suppose we have a horizontal layer, we have one horizontal layer, then we are having one vertical metal layer, then another horizontal metal layer. Okay. So I have two layers in which I can run my lines horizontally, and one layer in which I can run my lines vertical. So now I extend my extended problem becomes something like this: that when I merge two nets into a horizontal composite net, that is what we did in our composite algorithm. Yesterday we discussed about that yesterday evening in detail about that, how to make a composite net. The composite net can be laid out either in layer 1 or layer 3, because layer 1 will be horizontal, layer 3 will be horizontal, in between layer 2 will be vertical, and that is what three-layer routing is. Layer 1 will be horizontal, layer 3 will be horizontal, in between the layer 2 will be vertical. So when you make a composite net, as per your Yoshimuraku algorithm, you can lay out this composite nets in layer 1 or layer 3. Okay, so layer 3 together on top of the other, there is some relative location. So let me talk about that. So this layer 1 and 3 both allows horizontal segments to be run. I can consider them as two composite nets, and I can run them together in two nets, in two layers. Okay, so the concept of is something like this. So in the conventional net merge algorithm, what we do is we merge the nets so that the nets which are merged are assigned to a single track on a single layer. But here what we are trying to do is that such composite nets, we are again trying to merge them to form a super composite net. Are you getting? One is we try to merge the nets and make a composite net. That is what net merge algorithm told yesterday. But there we had only one horizontal layer. But here we are having two horizontal layers. We can put it in layer 1 or layer 3. So once again, what we do is among these composite nets, if you are able to merge them and make them as super composite net, and the scope of super composite net, one can be laid in layer 1 and one can be laid in layer 3. So like you see in the Yoshimuraku algorithm, when I merge two nets, it means that their horizontal constraints do not conflict. Then the vertical constraints also do not conflict. So they can be put on the same track in the same layer. Now, suppose I have run Yoshimuraku algorithm like this. I have several composite nets. So the early example is that you saw yesterday's discussion. There were 5 such composite nets. We laid it on 5 layers. Okay, we start with 4, 10, 1, 7, 5, 6, 9, something like that. Now, what we look at the now look at is something. This 5 composite nets, we can merge 2 of them together, remembering that we have another additional horizontal layer with us. So, do we have 2 composite nets which we can possibly place on this M1 and M3 in the same location, same track position? That will of course reduce our total channel height, and that is what we are looking at. So, we are basically trying to reduce the channel height. So, we are trying. We reduce the number of supercomposite nets. That's the objective here. So we are trying to merge the composite nets to create something called the super composite nets. There is an additional step here, which means we'll be once again running the same net merge algorithm. So our objective is to reduce the number of super composite nets now, not the composite nets, to reduce the number of super composite nets in this 3-layer solution. So our super composite nets basically means a set of composite nets which are placed on the same track, but possibly on 2 different layers. So now our target is to minimize the number of composite nets, which means minimizing the number of tracks. If you can reduce the number of tracks, we can reduce the total number of area of routing, because the height of the channel can be reduced. Okay, so this is the idea here. So what I said is a 2 composite nets. Okay, and I make a super composite net that can be assigned to 2 different layers on the same track. Okay. But maybe 2 different layers, M1 and M3. So without going much into detail here, I'm just giving you the overall approach. Use some kind of track ordering graph. We'll be using a new graph called the track ordering graph, which means one level of abstraction beyond what was used in the Yoshimura-Ku algorithm. In the basic net merge algorithm, we are using the graph depicted the vertices that we can merge together to assign them on the same track. But now we have another high level graph representation where these composite nets are further merged to create something called a super composite nets. So what I'm trying to say is basically at the end of the Yoshimura-Ku algorithm or the net merge algorithm, you'll be having the super nets as a solution. That one you try to, that will be the input of this new algorithm, that is the new graph what I am trying to make. That is, I am talking about the track ordering graph. Okay, so now we have a choice whether we can use metal layer 1 or metal layer 3. I have 2 super composite nets. Let us say M1 and M2. Okay, so they can be laid out in M1 or M2. Say I am having 2 super composite nets, C1 and C2. So I can put C1 in metal layer 1 and C2 in metal layer 3, or the reverse. So I have chosen one which one to put below, which one to put up. So there are 2 layers, metal layers M1 and M3 available now. So whether C1 to put in M1 or C2 to put in M1. Okay. So that answer will be given by your track ordering graph. Okay. So that graph will reflect that. So the vertices of this track ordering graph will represent the composite nets of the. Let me show the track ordering graph. I hope you remember this one. The top one, A diagram, is the one what we got as a solution at the end of the Yoshimura-Ku algorithm. So after implementing Yoshimura-Ku algorithm, you will get some solution like this. Okay. So this example showing the graph, example graph without going into some details. Okay, I'm not going to talk about how I got this. I'll talk about only this track routing algorithm. Okay, sorry, track graph, ordering graph. So this was a channel routing problem which was given, and this was the corresponding track ordering graph. Okay, that which track can be placed before the other. Okay, so how this track ordering graph is done is basically you will be using once again the Yoshimura-Ku algorithm. This is pretty straightforward. So from this you can see this track. Okay, this is a graph. This T1. okay, can go first, or T2 can go first. And there is no overlapping dependency between T1 and T2. Like this, there is no dependency between T2 and T3 and T4. But sorry, but T2, there are dependencies, T1 and T5, and T2 and T5, T3 and T5, T4 and T5, T2 and to T4, and T2 to T3, and T1 to T3 is also there. Okay, so this graph will tell you how many tracks are required, and the dependency, which one will be going to the top. Okay, track T1 is going to the top. Then you have T2. T1 and T2 can be top. You can put T1 on top or T2 as the top. Both can be done. Okay, because T1 and T2, because they don't have any kind of dependency. That's what I just explaining to you. Okay, like that among T3 and T4, anyone can be top. So now we are having a graph representation like this. Okay, so among this this T1 and T2, T1 and T2, they are independent. Now you see, this is a solution of you get out of the Yoshimura-Ku algorithm after applying this algorithm to the layer 3 model. Now I have not shown some of the steps. You can work out the steps yourself, because Yoshimura-Ku algorithm is known to you. Okay, so we'll be getting a final track ordering graph like this. And this graph says that T1 and T2 does not have any kind of dependency, the previous one. Okay, which means you can place T1 on top of T2, T2 on top of T1, or even we can put them together on the same track, one above the other, one in M1 and the other in M3. There is no constraint between them. Okay, so now I can have a graph representation like this, what is shown here. Okay, so this is something interesting. Looking into the scenario from this graph, the previous graph, what you can do is you can create a scheduling table like this. Okay, so this was the track ordering graph. From the track ordering graph, you can make a scheduling solution. So what we say, you can put T1 on top or T2 on top. Okay, both go hand in hand, T1 and T2. And like there is no dependency between T3 and T4 also. So no dependency between T3 and T4 also. So I'll make T3 and T4 and then T5. So from where I have to start, I have to start with the T1 because there are no edges which are ending on T1 or T2. So I can start with the T1 or I can start with the T2. Both the things I can do. After that, but I can't start with the T3 and T4. But when I want to lay T3 and T4, I can lay them together. Okay, this is what can happen here. Okay. And then finally T5 remains, and T5 will be done at the third step. Okay. So I can have a graph representation for this. From this optimal scheduling table, we are having a track representation for this. Now we are having so many combinations. You can place T1 first, then T3, then T5, or T1, T3 and T5, T1, T4, T5, T2, T3, T5, or T2, T4, T5. So all these things are represented as a path here. Okay. So I'll start and T2, T1 at the top and T2 at the bottom. Okay. And then T3 at the top and T4 at the bottom. I can go like this. Okay. And then T5 at the top and there is no nothing. Okay. Or I can have T1 at the top, T2 at the bottom, and then I will go down T4 at the top and T3 at the bottom. So I can go after this or like this. And once again, T2 at the top and T1 at the bottom. You can go this way, or you can go this way, or you can go this way. There are so many options here. T5 also you can put top or bottom. So if I include all these things, there will be 8 paths here basically. So among this path, which one will you choose? So here is a headache for us. So I can put T1 in M1, M3 and T2 in M1, or T2 in M3 and T1 above. So all these possible combinations are. So we have so many alternatives, and the edges will indicate the corresponding cost. So these edges indicate the cost. This two indicate the cost. Those one indicate the cost. Okay. So say given this graph representation, we try to find out the path which gives you the lowest cost. Like here, the lowest cost will be which one? Which one will be the lowest cost? This is 2, this is 3, this is 2, this is 3, this. Okay, this one, I'll start from T1 on top, T2 at the bottom. Then I'll go here. Okay, so the cost of this is 1. You can see that this 2 is for this cost. Okay, this is for the slanting line. This is cost is 1. Okay, T4 at the top and T5 at the bottom. And from here, I go here. Okay, this is T6 at the top. I will not go like this. Not T6, okay, something like T6 is there, it is at the top and T5 at the bottom. So I'll end here. So this is the one which is having the lowest cost, which means the cost will be only 2. If I add the edges cost, it will be only 2. Okay. So this will be your final solution in 3 layers. So this is the basic idea behind how we extend the Yoshimura algorithm and extend it to the 3-layer model. Okay. Now we'll talk about the switch box routing. A brief look once again. We shall not go look into the detail of any of these algorithms because of 2 reasons. The number one, in switchbox algorithm particularly, no systematic algorithm exists. Most of the algorithms that have been proposed and are used for switchbox routing are based on some rules and some heuristics, which are not very interesting to discuss here. Okay, so when you want to to learn, okay, you can refer to any of the standard books that is simply based on some heuristics like greedy algorithm. Will be doing that. Okay, switchbox routing, you can recall in some problems where the pins are located on all the 4 boundaries of a rectangular region. Okay, so the main objective here is to it is more difficult than the channel routing algorithm. Okay, so here the main objective of the channel routing algorithm is to minimize the channel weight, whereas the main objective of the switchbox routing is to ensure that all the nuts are routed. That is the idea here. Okay, so it can be an extension of channel routing problems. We are having the channels on all the sides, so the terminals exist in all the 4 sides. Now one thing you need to understand, now in the channel routing problems, what we do is there are so many good algorithms available. Their objective is to minimize the channel height. But in switchbox, you see the constraints is different. You see pins are coming from all the 4 sides, which means that it is not easy to compress the size of the switchbox. If you want to compress, we need to work on all the directions. So maybe there are blocks on placed on already placed on all the 4 sides. So switch boxes shall not have appeared in a standard cell based layout. Okay, there we have only channel, but for full custom design, full custom based designs, uh, style switch boxes may appear. Okay, because they once they appear, the blocks are on 4 sides, are all fixed, so you cannot move them around. So your objective is to not to reduce the area there, the height, but to ensure that 100% computational of routing is there. So the objective is completely different, and that is what is given here, the second step. Okay, the main objective is to ensure that all the nets are routed. So there are many algorithms which has been proposed. So one may be a greedy router, as I told you, based on a set of simple rules, or we can have rip up and reroute algorithms. You start, do it. If there is a congestion, rip up and reroute. Okay, remove some of the nodes which have been laid out, again retry. And there was another interesting approach which was based on computational geometry. Some algorithms. This is called as Beaver algorithm. Okay, this Beaver algorithm is quite popular. Okay, it's a quite popular algorithm in that sense. So I'm just showing one example of Beaver algorithm alone. Okay, this is the one. Showing one example. This of the switch box. You can see there are the pins coming from all the 4 sides. Pin coming from top, left, right, bottom. Okay, and you have to interconnect all the pins. Okay, which means you have to interconnect the pins based on the net number. So net 2 here, net 2 here, you are having 2 here, you are having 2 here. So all those things need to be connected. Okay, so that the constraint remains that horizontal and vertical lines may be on 2 different tracks. It's basically a 2-layer routing model. Okay, solution is shown. So the horizontal connections may be on metal layer 1, and vertical connections may be on metal layer 2. So now you can have multi-terminal nets also as well. So this is final solution of the switch box. I've not explained how this is done, but this is done with alpha of a Beaver algorithm. Okay, Let me summarize some of the algorithms here. Then after summary, we'll be talking about the extension, one completely different algorithm. With that, we'll stop. Okay. So to summarize this detailed routing algorithm, this is a summary of all the detailed routing algorithm. You can say by channels or switch boxes. The routing models, the detailed routing algorithm, routing problem is solved by routing the channels or routing the switch boxes. The routing results may differ based on the routing model used. It can be grid based, or it can be based on assigning layer of different net segments. Okay, so here the main objective is to minimize the height of the channel. Okay, sometimes main objective is to minimize the height of the channel, that is the channel density. Sometimes we are interested in reducing the length of the routing nets, which means that may be a critical path. So if you are able to reduce the length of the critical path, routing net in the critical path, you will be able to reduce the delay. If you are able to reduce the delay, you will be getting higher performance, which means the speed will go up. And sometimes the number of vias. Okay, so minimize that depends upon what kind of thing you are doing. So whenever you are making a via connection, this vias, okay, via, it means that you are putting some kind of drill. Okay, uh, so I mean inside the fabrication process you use a metal to connect one metal to the other metal layer. So what might happen is once you do this, you have an additional resistive and capacity effect. There is a bend and the resistance will change. So less the number of beavers is better. That is we need to reduce the number of vias basically. That is one criteria. And of course switch box routing, as I said, the objective is to mainly determine the routability, not to minimize the area. So now we shall be looking at a new way of routing called over the cell routing. Now this over the cell routing appears for a standard cell kind of a layout, standard cell. Okay, we have discussed about the standard cells. You remember that. Okay, over the cell routing appears only for the standard cell routing. You cannot do it for full custom design. You can do the over cell routing only for over the cell routing is applicable only for standard cell kind of layout. So let us try to understand the motivation behind this over cell routing and some of the basic algorithm and some of the algorithmic steps which you can follow for this. Okay, so the idea is like this. So I'll be talking about the algorithm now, even though I promise that I will not be discussing in detail, but over this is very quite interesting. That's why I want to talk about that. Okay, so the idea is that the area outside the channel, sorry, we are trying to use them in the interconnection. Inside the channel, there will be some area you are using it for interconnection, and how to do that? That is what we have discussed so far in the detailed routing, channel routing. But outside the channel, what is the area outside the channel? How we can use them to try to use them for interconnection? So because the additional layers are not used here, we are not going to use any additional layers, but uh, we'll see how to do that. Okay. So the use of area outside the channel to obtain the reduction in channel height, routing the channel over the cell rows is possible due to limited use of second and third metal layers. Okay, this means something like this. Sorry, channel. What I mean to say is that I am having a standard cell kind of layout. This is a standard cell kind of layout, and you are having only channel. There will not be any switch box. Okay, so this is your channel. Suppose in a three-layer, we are in a three-layer channel routing. Okay, in this channel we are having three layers: metal layer 1, metal layer 2, metal layer 3. If I say three-layer channels are routing, so inside the channel here we are using HVH model. So there are three metal layers. We are laying out wires on these three layers inside the channel only. Inside this channel only. Okay, but not on top of these regions. You'll be laying the channel layers. When I say metal layer, three metal layer, within this channel region only, you'll be laying the metal layers. Metal layer 1, metal layer 2, metal layer 3. But what will happen here? What about on top of these regions? What are there in this region? In this region, we are going to have some logic blocks. Okay. So that is quite interesting. Here actually the devices are fabricated in this region. The devices are fabricated in this region also. The devices are fabricated. The devices in the sense it can be transistors, the logic blocks. It can be a simple transistors or it can be gates. All these things. So on top of all these logic gates or transistors, there may be metal layers. It's quite obvious. So on top of it, maybe one of the metal layers is available. Okay, and that metal layer is free here somewhere. So why not use some of the connection for between two points? For example, here I am having a net. Here I am having a terminal. These two terminals, instead of running a track here in this channel, I can use the metal layer in this area. Okay, I can connect it. So this is called as over the channel routing. So this is within the area, within the channel routing, and over the channel there is a metal layer which is not in the channel, which is outside the channel area. So that can be used here. So let us see something like this. Okay. I want to connect this point to this point, as I told you, this point to this point. So there is no need to run a metal layer, a horizontal layer and vertical layer like this. So I need a vertical layer, one vertical line. I need another vertical line. I need one horizontal line. Okay, I'll be using spaces in my vertical metal layer 1 and metal layer 2 for that. So instead of that, I can use this area, the metal layer, which is available in this logic blocks. Okay. So similarly, I want to connect. I have a way of connecting them. So why not? We say, for example, I want this point to this point, and I find a free space here. I want to connect this point to this point. Okay. I'm having a free space here. Okay, there is a free space, there is a free space, which means there is no connection. So what I can do is I can connect these 2 points and connect these 2 points and I run a line. That's all. I need only one vertical connection. That's all. I will be able to make the connection here. Okay. So this is uh, I find why you can think, sir, you are anyhow going to run a vertical line. Why don't you run a vertical line and connect these 2 points? Basically, you want to connect these 2 points. Why are you talking about running way roundabout way like this? But the problem is, in this area, this channel may be highly congested, which means already there are some other nets and there will be some horizontal tracks are running here. Track 1, track 2, track 3, track 4, track 5, track 6, all are running here. Okay, so it is highly congested. So what I can do is maybe I want to reduce the congestion. So I can take it out from somewhere here and I can connect like this. Okay. So if there is a congestion, I can make use of this. So as a part of the net, I can lay out on top of this. So this is why it is called over the cell routing. Over the cell routing. Okay, this is cell. This is a standard cell, and this is a standard cell. And over the standard cell, we are doing the routing, and this is why it is called as OTC, over the cell routing. Okay. So let me talk about the basic steps. And as I told you, we'll be talking about the algorithms. So how to do the OTC routing with the help of an algorithm. So I'll be talking about these steps that will complete the discussion. So there are several algorithms which have been proposed for the OTC or the over the cell routing. So I am suggesting some basic steps in one such approach. In the first step, we are doing some kind of net decomposition, which means if you have a multi-terminal net, you partition them into a set of 2 terminal nets. So that we have already discussed. If you are having 3 terminals named as 222, which means multi-terminal. So what I need to do is again, as we have discussed in the left edge algorithm, basic left edge algorithm, based on the x coordinates of the leftmost terminal, you can partition them into 2A, 2A, 2B, 2B, 2C, 2C like that. Okay. So then the nets you classify as one of the 3 different types. So we need to first we need to decompose that net. You cannot do this algorithm for multi-terminal net. So wherever we are having a multi-terminal net, that multi-terminal net is to be partitioned into a set of 2 terminal nets. Okay. So this is applicable earlier on the other algorithm also. Okay. Once we have divided that into 2 terminal nets, okay, we will do the net classification. The nets you can classify as one of the three types. Type 1, each net is classified into one of the three types. Type 1, there is a vacant terminal directly opposite to one of the terminals of the net. So it's like this. Okay, there is a vacant terminal opposite. This is net 1, and there is a vacant terminal opposite to this. So that is called as type 1. Type 2, there is a vacant terminal between the two terminals of the same of the net. Between the two terminals of the net, I will show like that. Okay, so I am having terminal 2, terminal 2. In between terminal 2 and terminal 2, I am having a vacant terminal. This is type 2. Or they need not lie in the same boundary. They can lie in the opposite boundary also. I am having terminal 2, 3. I am having terminal 3, and in between I am having a empty terminal. Okay, so there is a vacant terminal between two terminals of the net. Between two terminals of the same net, two they are connected by a same net, two terminals of the same net, we are having a vacant terminal. Between 3 same net, two terminals of the same net, we are having a vacant terminal. This is called as type 2. And type 3, if it is not coming under any of the thing, we call it as type 3. That's all. Okay, so we are having three types of nets. Okay, so type 1, type 2, and type 3 we have discussed. So type 3 means none of the things exist. Okay, so once we have completed the classification of net as type 1, type 2, and type 3, we go for the third step, assigning the vacant terminal. Okay, vacant terminal assignment, it's the basic idea. Okay. Very interesting thing. Vacant terminals are assigned to each net depending on its type and weight. And how do you define the type and weight? Or weight? It can be defined as the improvement in the channel congestion that can be achieved if you do the over the cell routing for this net. So there are many ways to make an estimate of this improvement in congestion. Like what I mean to say here is that vacant terminals are assigned to each net, means like so when you say, let us say that this is assigned, okay, assigned to 3. This vacant terminal is assigned to 3. Okay, this vacant terminal 3, sorry 0. This is a vacant terminal. Assign this 3 vacant terminal to the net 3. Okay, you can assign this vacant terminal 0 if the net here is congested. Okay, in this area what I have shown here, in this area the net is congested. Okay, so what do? You do over the cell routing from here, from the terminal 3 to the vacant terminal here. Okay, from here to here, and from here to you move out. Sorry, move out to here. Okay, and then you can connect it this way. So you are avoiding the congested region. This region is congested. This region is you are avoiding. Otherwise, you'll be running like this and doing this. So you'll be unnecessarily adding one more track. So you are avoiding the congested region. So you are moving it out. So this taking a vacant cell, taking up from there, and from there you can do another over the cell routing. So, and one thing is there, during this over the cell routing, you are not seeking from layer one layer to the other. The entire net can be done on the either both horizontal and the vertical. They can be laid out on the same metal layer. This is the difference, because in the over the cell routing, you are not allowed to use the wire connections. Okay, you are doing it on the same metal layer, right? So after this, you go to the step 4. Step 4 is over the cell routing. So vacant terminal assignment are assigned based on depending on its type and weight. So the weight of the net is defined as the improvement in the channel congestion possible if this net can be routed over the channel. So this is what I explained. So if I am going to increase here, the congestion will increase. If I am going to lay out net from the terminal 3, if I am going to connect to a layer like this, okay, not the layer, to the some horizontal segment, if I am going to assign that, okay. if I'm going to route the net 3 here, so I am avoiding the congestion. So it is having a weight, a good weight, and that can be assigned. So this can be avoided with the help of this vacant net. So the vacant net will be given some weight. This will be given more weight. If you are having 4 lines running, then if you are going to connect this net, this is terminal 3 to the net here, another to the net 3 here, then the congestion will become 5. So this vacant cell will be given a weight of 5. That is what I mean by weight here. Okay. So after this, you can the selected cells are assigned next exact geometric paths for routing in the area over the cells. This is called as over the cell routing. So step 4 now you says that you do the over the cell routing. After you identify the vacant terminals, and in the last step, uh, okay, final step, you select which net segments can be routed in the channel, which net segments can be routed over the channel. This is very important. Which net segments you are going to route in the channel, okay, in the channel, and which net segments you are going to route over the cell. Okay, so this is very interesting. So once you make this decision, then you have an idea which one will move to within the channel, and which one will be move not within the channel but outside the channel. Okay. So let me take an example to illustrate that. Okay. Not this one. This is the this practical example which will give you an idea how this is done. So let us say this is a typical snapshot of the standard cell design cycle. Here I have four cells, which are placed. Cell 1, standard cell layout, cell 1, cell 2, cell 3, 4 cells are placed. Here 6 cells are placed. Okay, and this connection what I am showing here, okay, this blue color connection, what is shown with the help of the pointer. Okay, this is actually a feed through cell. Okay, so I have not connected here. Okay. So this is also a closed rectangle. If I make it this is a closed rectangle, then this is also a part of the standard cell layout. So this is a feed through cell. Okay, the feed through cell will not be assigned for any logical block. We have already discussed that in the first unit. Okay, so suppose this is one solution. So here you can see which nets are connected to which nets. Which nets are connected to which nets, which are shaded or nets with some number, and the which are not shaded, they are vacant nets. Okay. So this solution is obtained based on some greedy routing algorithm. So you can see which nets are connected to which nets. You can see this net is connected to this net. Okay, this terminal is connected to this terminal. This terminal is connected to this terminal like this. This terminal is connected to this terminal. So I'm having a dog leg also. You can see from here I'm running a horizontal layer and another horizontal track. So I'm using two horizontal tracks in the same channel. So I will say this is a dog leg. Okay, and I'm connecting this. So greedy channel router allows dog legs also. We know about that. Okay, so you can see how many tracks are required here. How many tracks are required? This is track 1, track 2, track 3, track 4. So maximum 4 tracks are required. So it requires that okay, 4 tracks are required. So sorry, here there is 1, 2. So this is a mistake here. This should be brown. So there are 3 here. Okay. So now this problem, if you do it over the cell routing, okay. So the possible solution will look like this. I'll show in the next slide. Okay, this is over the cell routing. So over the cell connections I am showing in red. Okay, this over the cell connections are shown in red. Okay, and the channel routing are shown in brown and blue. The conventional, we have been using this for all the discussions so far. For all the discussions on routing, we use this. This blue color is for vertical channel in the metal layer 1, and brown color is for horizontal track in some other metal layer 2. Okay, over the cell routing is shown with the help of the red color. Okay, you see this pin. See, this is the idea. This is I'll be using this track instead of this. I'll be using a track, horizontal track here. If I do like this, so but this pin is a empty pin, vacant pin. So what is this type? Is it type 1 or type 2 or type 3? It's type 1. Type 1 is we are having a vacant pin opposite to the occupied pin. So what I do, I will simply write in a connection, and from here I'll do the over the cell routing. So I'll be able to remove this. I'll be able to remove the congestion. Okay. So similar to this also, from here I am connecting this, and in between I am having a say this is in between I am having empty cell. Okay, but here I will directly connect. Okay, this one. Okay, this is connected to this. Okay, and from here to here also I can do like this. I'll show one by one. Type 1, type 2, all these stories. Okay, type 1 I will just now explain. Maybe type 2 also I will show. So this is the type 1 problem. Okay, there is a vacant pin just opposite to it. So use it for the vertical segment. So similarly, you can try. You are avoiding. You can see you are avoiding this horizontal segment. Okay, this horizontal segment can be avoided here. Similarly, you can see this connection was there. See here, from here to here, I'm having one connection. Okay, so this is a dog leg I was talking about. From here, there is a horizontal track, and there is another horizontal track. This is a dog leg. Okay, so this pin and this pin are having the same number. Okay, so between the nets of the same number, I'm having another pin. So this is type 2. This is pin number 3, and this is also pin number 3, and in between I am having a vacant pin. So this is type 2 pin. So what I can do is, instead of doing a dog leg here, from here I will directly connect here, and from here I will do the over the cell routing. See, so the congestion is removed. You can very well, it is very simple here. It is so congested. Here the congestion is removed. And moreover, here you need 1, 2, 3, 4 tracks. Here you need only 2 tracks. Okay. So the channel congestion is reduced to a greater extent. Okay. So in this way, you can identify all the type 1 and type 2 connection. But again, do not go blindly using what do you say, that is routing for type 1 and type 2. All of them can be use them only if it reduces the channel congestion. Okay, with respect to some cost metric. So once you do this, you will get a final solution. This is a final solution like this. So here, instead of 4 tracks, what we are doing, what we require in greedy channel router, I need only 2 tracks, which means the rows can be brought, this row and this row can be brought closer together. Okay, which means I'll be reducing the channel height. Okay, so the other connections can be carried out over the channels, over the cells. Okay, so now in general, in fabrication technologies, there is another interesting thing. There is another interesting thing I want to convey to you. In fabrication technologies, what will happen is you will not be having only one metal layer. That is, here I am going to have the blocks, logic gates, logic blocks. I am going to have cell 1, cell 2, cell 3. I will not be having only one metal layer. I'll be having metal layer 2, metal layer 3 also here itself. So what I can do is, I can do all this horizontal channel, vertical routing, horizontal metal layer 1, metal layer 2, metal layer 3. Okay, metal layer 1 horizontal, metal layer 2 vertical, another horizontal metal layer. All these things can be done in this over the cell itself. So in that case, we don't need this channel itself, and that is what is called as channelless routing. Okay, that we have discussed in first unit. There you may not have got any idea about that, Glory. Okay, but now you will be able to understand this in a much better manner. Wow, I say, how can we do this over the channelless routing? So here, if there is a channel, I can route, but there is no channel. I'll be just joining them together. But what will happen is, in the cell area, when I am placing the logic blocks, when I am fabricating, okay, you are you are going to have so many things. Okay, so many metal layers are there. Okay, so in the fabrication technologies, where there are more than 3 layers are available, that is multiple layers may be available in the logic block itself. So you can possibly do the entire routing on top of the cell. So top of the cell routing, over the cell routing, you can do this. So there is a conflict. This is that is called as channelless routing. Okay, so You need not need any channel for this. So this completes our discussion. Okay. So one thing I am repeating greedy channels, although it appears to be very simple, that it is still considered to be one of the powerful tool because it can handle the problem instances where there are cycles, where there are vertical constraint graph, all those things. So greedy channel router is one of the very powerful tool. So this completes our set of lectures on routing, all the routing, okay, all the physical layer. We started with the partitioning, floor planning, pin assignment, placement. We spent a lot of time on placement. On routing, we spent three lectures on grid routing, 4 lectures on global routing, and another 4 lectures on detailed routing. So I complete here. We'll be talking about the special routing, and that some other topic we will complete the second unit by today evening or tomorrow morning. We'll complete the session.
Okay, sir.
Okay, let me take the attendance.
Okay.
Okay, thank you, ma.
Thank you, sir.
Bye.